All right, 1.5b, College Algebra. We are on application of functions, example 3, bottom of page 122. And talking about a car here. So we've got Tracy and Graham drive away from a campground at night at right angles to each other. All right, so basically we've got one of them going this way and one of them going this way, right angle here. All right. Tracy's speed is 65 miles an hour. And Graham is a little bit slower grandma driver. And he's going 55. So he's going this way and Tracy's going this way. All right. Express the distance between the cars as a function of time. Whenever they say as a function of time, what they mean is this. Function of time means the t for time is going to go there. So you're going to write an equation and you're going to have f of t as part of your equation, or d of t, or whatever. All right, so if we're talking time and they're going 55 miles per hour, that means that as this, we're not talking necessarily 55 miles here and 65 here. We're talking that as long as he goes 55 miles an hour and she's going 65 miles per hour, the distance between the two is going to get bigger and bigger and bigger. So the distance, depending on time, is going to be that far. Okay, that's what that means. The distance dependent on time. If that time is 1 hour, they're going to be a certain distance apart. If the distance was 4 hours, the distance is going to, or the time is 4 hours, the distance is going to be even greater. So, distance dependent on time. So if we make the speeds dependent on time, this is actually 55 miles in an hour, but it's also 55 miles times however much time goes by. And the same is true here. 65 miles in an hour, but it's 65 miles times how much time. So if it was 2 hours, Tracy would have gone 130 miles. Okay? So what we've got is this distance here. If we use the formula, the distance formula, or the Pythagorean, a squared plus b squared equals c squared, then we could write this equation as distance dependent on time, that's my hypotenuse, is going to equal b, or a squared plus b squared, so it doesn't matter which one you pick here, 55t plus 65t squared squared. And there's a formula there. That's the formula. I can always figure out how far it is between the two cars if I know the amount of time that's gone by. So let's say this was 3 hours. I put a 3 here, times it times 55, square it. 3 here times 65, square it, add them together, and that's going to be this squared. Okay, so I can figure out how far they're going to be dependent on how much time they've been driving, and that number will get bigger and bigger and bigger. So, if we wanted to go a little bit further, we could take the square root of both sides. So now we have 55t squared plus 65t squared, square root of, equals d of t. Okay? So if we squared 55 and 65, we would have 3025 t squared plus 4225 t squared equals d of t. Now I can add these because I've got common variables. So I've actually got 7250t squared, square root, equals dt. And if I take the square root of 7250, I get about 85.15 t, because I took the square root of that, equals dt. All right, so what I did is I took this formula up here, which would work, and simplified it. So if I want to know how far apart they are, all I have to know is how much time has gone by. So for instance, if I want to know how far they are in an hour, I put a 1 here. So they're going to be 85.15 miles. If I want to know how far they are in 6 hours, I put a 6 in here. 6 times this will tell me how far apart they are. So what I've done is I've come up with a formula so that no matter how much time has gone by, I can determine how far apart they are based on how much time that's gone by. Okay, so that's what they're asking you to do in that first example. All right, let's look at example 4. Okay, so in order to get what they're asking for in story problems, it's always good to draw a picture so that it kind of helps you there. So we've got the sound shop has 20 feet of dividers. Okay, so we've got this divider that's 20 feet long. Okay, it goes from there to there. And these dividers have little notches there so you can kind of fold them. All right, so we're looking for a divider to make a rectangular area of this room that I have right here. And it says if a corner of the store is used for storage area, the partition only need to form 2 sides. All right, so I've got this thing here, right here, that I'm putting, the blue, and the total distance from here to here is, again, this 20 feet that we had measured. Okay, so what they're asking for is express the floor area of the storage space as a function of the length of the partition. All right, so what they're doing is if we made this partition this big, 1 foot by 20 foot, this would be 20 square feet, right? If this were 2 feet and this were 18 feet, this would be 36 square feet. So see how even though the length is the same, the area that you're able to use is bigger. This is 3 times 17. That's 51 square feet of space. Okay, so you're getting a more space there. Then you've got 4 and 16. And this gives me 64 square feet of storage space. And let's say I went 8 here, and that leaves me with 12. That gives me 84 square feet of storage. So see how the storage space gets bigger and bigger, all right, and we're still talking 20 feet of partition. All right, let's go to, let's say this one is 10 and this one is 10. Whoa, that gives me 100. And if I go 11 and this is 9, now it's getting smaller again. So the maximum amount of square footage that I'm going to get from this partition is somewhere around here, but I don't know exactly, okay, what it is. So all I know is that I have basically come up with a graph that as one side of the storage gets bigger, the other side has to get smaller, right? So if we start out at 20 and we go, the other side is 1 foot, we have 20 square feet. And as we make this smaller, let's say we make this 10, the other side is going to be 10, and it's going to give me 100. Okay, so it's going to give me a lot more storage space. So what we're trying to do is come up with a formula that is going to help us determine the best way to put this partition together. All right, so we're looking at the area that this partition is going to make, and we're going to have one side. Okay, so we're looking at the area given the length in feet of one of the sides. So actually of both of the sides, because one of the sides of it's going to be x, the other one is going to be 20 minus x, because it's 20 feet long total. So no matter what one length is, the other one's going to be the 20 feet minus that length. All right, so we're looking at those. So the area, what is the area of a rectangle? Length times width, right? Well, we're not interested in length times width. We are interested in length times width. So we're interested in x times 20 minus x. That's our area of this rectangle. And if we do the math here, there's my formula. Okay? So I can put in numbers for x right here, doesn't matter what numbers, and see what my area is going to be. Okay? And I can find out, how much room that this partition is going to fill up. And I want it to be the maximum because the B part of this says find the domain of the function, and it says use the graph shown at left to determine the dimensions that maximize the area of the floor. Alright, so C, you can see that the maximum area of the floor is going to be 100 square feet, my Y value, given that one side is X, and actually so if you find X is 10, then this Y value is going to be 20 minus 10, which is 10. So 10 times 10 is 100. And notice that the maximum value is when X is 10 and Y is 10. That gives you 100 square feet when you plug that 10 in for the X here. Because we've got 20 times 10 is 200 minus 10 times 10 is 100. 200 minus 100 is 100. So find the domain of the function. What does that mean? We're trying to find out what are the possible numbers that we can use for the x value. Well, can we use 0 for x? No, we can't put 0 in for x because the partition, if our partition is 0, then it's going to be 20 feet long and it's not going to be any wide because the width is going to be 0. So, but it could be 0.1, it could be very, very tiny, the distance between here and here, and then this length here would be almost 20. So as long as this first number, x, is bigger than 0, our y value can be a number all the way up to 20, but it cannot include 20. So this could be a 3 by 17, it could be a 6 by 14, it can be all those numbers that add up to 20 that are between 0 and 20. You couldn't have like -6 and 26 here. Yeah, those add up to be 20, but you can't have a length that's negative. So you know it has to be bigger than 0 and less than 20 here. So that's your domain. So you see how that works? You can kind of come up with a way to figure out some more intricate math problems using this max-min kind of stuff. And I know I kind of went fast over it, and it's probably confusing, but we're going to keep going, and it'll start coming together a little bit. Alright, I'm going to save the functions defined piecewise in the next video.